This is part 1 of 4.2 Observational Studies and Experiments. An ADHD linked to lead and mom smoking, study done by Karen Barrow. Cincinnati Children's Hospital Medical Center surveyed over 4,700 children between the ages of 4 and 15 and their parents. Over 4% of the children included had ADHD. The researchers found that those children whose mothers smoked during pregnancy were over twice as likely to develop ADHD than the child whose mother had not smoked. So, based on this study, just what we know from this, should we conclude that smoking during pregnancy causes an increase in the likelihood that a child develops ADHD? Explain. No. I guess, and we're saying that there really isn't any way to prove smoking is the cause, and we'll get into that a little bit more in a second. One reason is confounding. Confounding occurs when two variables are associated in such a way that their effects on a response variable cannot be distinguished from each other. Like we have the lead and mom smoking. We don't know which one had the effects of ADHD. It could be a little bit of lead, a little bit of mom smoking, maybe a lot of lead, a little smoke. We don't know. That's confounding or kind of confusing. That's how I think about it. It's confusing the data. All right. More confounding things, genetics. People have different genetics in them. Misdiagnosis of ADHD, other health factors like diet or drinking or exercise or whatever is going to change just our medical or the medical stuff going on here. Is there any way to prove that smoking causes ADHD? Well, to prove something causes something else, you need to have an experiment. So an experiment here, we would assign some mothers to smoke while pregnant and others to not and study effects. Obviously that's unethical, not going to happen, no one's going to let us do it. Likewise, parachutes, do they really work? It's an observational study because we're not going to have anybody jump out of the plane with no parachute. That's not ethical, it's not legal. So experiments work sometimes, but some they can't. We can't use an experiment with these things just because of the effects. So an observational study looks at individuals and measures variables of interest, but does not attempt to influence their responses. So they're just kind of watching. They watch, write down data, watch more. Where an experiment delivery imposes, I like that word, for some treatment on individuals to measure their responses. Here the difference between an observational study and experiment. Observational describes and compares groups and examines relationship. Can't gauge cause and effect because of confounding. Whereas an experiment determines if one variable causes change in response. Well-designed experiments are only source of fully convincing data for cause and effect. And again, remember a response variable is the outcome of a study, and explanatory variable is to predict what is going on with the response variable. So if you want to think about it in terms of things we've done before, that's our y, that's our x, if we're talking about a scatter plot or something like that. Oh, we're here. Designing experiments. So we want to see if caffeine affects pulse rate. Here's our plan. Measure initial pulse rate, give each student some soda with caffeine, wait for a specified time, measure final pulse rate, compare final and initial rates. It sounds great. However, we have some problems, things that we have to nail down. So even if every student's pulse went up, we couldn't attribute the increase to caffeine definitively. We don't know how much caffeine we're giving. We just, the confounding variables, excitement of experiment, sugar and soda, something made them laugh, excited during their wait. A lot of different things can influence pulse rate. So we got to make it as controlled and as specified as what we can do. There are several steps we should take to solve this problem. First step is to conclude comparative experiment. That does not receive caffeine. So we have something to compare to. So we're going to have our caffeine group and our non-caffeine group. Otherwise, any pulse raising or lowering event could happen during the experiment by being confounded with the caffeine. For example, an amazing stats lecture during the waiting period would certainly raise pulse rates, making it hard to know how much of the pulse increase was due to the caffeine. Things happen, and you're not living in a bubble. So when we talk about experiments, these are the things we need to think of. Experimental units, small collection of individuals to which treatments are applied. If it's people, it's called subjects. It's who we're doing the experiment or what we're doing the experiment on. So in this case, it's students. And there are subjects because there are people. A treatment is a specific condition applied to individuals in an experiment. Here, it's caffeine versus no caffeine. We want to see the difference. That is our treatment. So it's either that or that. Factors um, are another way of saying explanatory variables. The amount of caffeine ingested should do something with the response and the pulse rate. Now, the level is the different, without saying the word levels, it's the different combinations or different looks that we're going to get of the factor. So, for example, for multi-factor experiment, we could give differently random groups chosen 0 grams, 10 grams, 20 grams, 30 grams of caffeine, and see very specifically how much caffeine affects pulse rate, not just if it is pulse rate. Again, we have our control group, we're getting no caffeine. The second step is to make sure that the two groups, caffeine and non-caffeine, are as similar as possible. And we can't know that, so we have to have randomized groups. We need randomization, replication, and control. So we randomly assign subjects to treatments, not treatments to subjects. It sounds backwards, but that is the way it goes. We create groups that are roughly equivalent at the beginning of the experiment. Random assignment ensures that the effects of uncontrolled variables are balanced among the treatment groups. Let's always randomize since there will always be other variables we cannot control or that we don't even think about. Randomizing guards against what we don't know and prevents people from asking, but what about this variable? So let's say we want 15 in each treatment. Experimental units are assigned to treatments completely by chance. Here are the main three ways that we can randomize. Using the hat method. Using 3 identical slips of paper. Notice how detailed it has to be. We even wrote identical slips of paper. Write A on half, B on the other half, mix them thoroughly in the hat, and have each student take a slip. Student with A drinks caffeine, B drinks soda without caffeine. Using technology. Number students from 1 to 30 or 0, 1 to 30. That's why they're all the same digits, so equally they happen. We use our random integer, and again, if you have the no repeat, do that. So use random integer, excuse me, from 1 to 30 to select 15 different numbers from 1 to 30. Repeated numbers should be ignored. You have to say what you're doing with repeated numbers, or else you're going to lose points on the AP exam. These students drink soda with caffeine and remaining 15 drink soda without. Using that number table, and again, here it is, 0, 1 to 30. Use a line from table D and read each 2-digit number. The first 15 different students drink soda with caffeine and remaining drink without. So it's all the same way of just getting to the same place. The second thing of an experiment after comparison is replication. We have to have an adequate number of observations to make sure that it's true. We don't want a small sample size to say, yeah, this is happening, but we don't know the whole picture. And again, we want the two groups to be as equivalent as possible. Then differences in the effects of treatments can be distinguished from chance differences between the groups. Replication can also refer to repeating the experiment with different subjects. This can help us feel more confident applying the results of our experiment to the population. So we do it over and over again, or we take more and more people, so we get the whole picture there and we make sure that it wasn't just a fluke, the first 10 people did this, or the first 5 people did this. Control means holding other variables constant for each member of both treatment groups. This prevents these other variables from becoming confounded with caffeine and from adding additional variability to the distribution of the response variable. So we want to make them as equal as we can. Prevents confounding. For example, sugar is an important variable to consider because it may affect pulse rate. One treatment group was given regular Coke, which has sugar, and the other treatment group was given caffeine-free Diet Coke, which has no sugar. Then sugar and caffeine would be confounded. There's a difference in the average change in pulse rates of the two groups. We wouldn't know which one affected which. So to prevent sugar from becoming confounded with caffeine, we need to make sure that the members of both treatment groups get the same amount of sugar, so the same pop. For example, reduces variability. For example, the amount of soda consumed is important to consider because it may affect pulse rate. If we let subjects in both groups drink any amount of soda they want, the changes in pulse rates may be from that as well. So it's harder to identify the effect of the caffeine. Again, everything needs to be as same as possible when we do this. So here the first set of dot plots show the results of a well-done experiment. Second set of dots shows the result of an experiment where students were allowed to drink as much or little soda as they pleased. The additional variability in pulse rate changes make the evidence for caffeine less convincing. So when we were allowed to drink, or they were set number of things, we can see a comparison. This is very similar to this group, but it's obviously less. So there's not as much change. Some people had a negative change. But when we just kind of do it random and you can have whatever pop you want, we have the two groups overlapping a lot of it. So we don't know what did what. Since the subject has been randomly assigned to the treatments, can the weight of the student be considered a confounding variable in this experiment? No, because we randomly assigned this. So there's probably weight. We can have heavier people on in both groups, ideally, and little people in both groups. So because the treatments were randomly assigned, it adds variation to the response. It's also important that all subjects in both groups are blind, meaning that they don't know which treatments they're getting. If they're getting the extra treatment or a placebo or anything else you think of. So otherwise, members of the caffeine group might suffer from the placebo effect. If they have caffeine and the others don't, well, they're thinking, oh, it has to be a caffeine. I gotta affect it like this, and not quite at what we're looking for. People measuring the response are also blind. The experiment's double blind. Now, this can happen if the people actually conducting the research study are not the exact same people that are giving the treatments to these subjects. And then we double blind and we know that no one's influencing either way. Summary. Comparison, randomization, replication, and control are the four principles of experimental design. They are important. You need to know that. Looks like we're getting to this word. Now, if changes in the explanatory variable are associated with changes in the response variable, we can attribute the changes to the explanatory variable or the chance variation in the random assignment. So again, from these experiments, we can do cause and effect. So we are multitasking researchers in Canada performed an experiment with university students to examine the effects of in-class laptop use on student learning. Participants were asked to attend a university-style lecture and take notes with their laptops. Half the participants were assigned to complete other non-lecture related online tasks. They were meant to imitate typical student web browsing during classes. The remaining students simply took notes with their laptops. To assign the treatments, the researchers printed 40 papers with instructions, 20 with multitasking, 20 without, shuffled them and handed them out to random students in the classroom. At the end of the lecture, all participants took a comprehension test to measure how much they learned from it. The results, students who were assigned to multitask did significantly worse than students who were not assigned to multitask. Kind of a dumb moment, but yes. Comparison. Researchers compared students who were multitasking and those that weren't. A random assignment. Students were selected by random, by seat location, for who would multitask and who wouldn't. Control. Experiment used undergrads from the same university. All participants listened to the same lecture and took the same comprehension test at the end. So most of the stuff was very similar. Replication. There were 20 students in each group. Although this is not a very large number of subjects, the difference in performance was big enough to determine that the difference was due to multitasking and not chance from the random variation. Right. Again, talking about our caffeine experiment, the results of an experiment are called statistically significant if they are unlikely to occur by random chance, meaning the difference is too big to take its chance. It actually had some effect on it. Again, we get back to our caffeine and the pulse rates. We had caffeinated today, non-caffeinated soda. You can see the difference in them. Obviously, when we look at the means of the two groups, Completely different. One's negative, one's positive. The difference is 7.71. Is this difference significant? Well, we have set numbers that work, and we'll deal with that second semester, but we need to figure out if that is significant. And here's our experiment. We write each person's increase in heart rate on identical sized slips of paper, assume caffeine has no effect, shuffle paper, deal into 2 piles, and we've done all this stuff before. Repeat process 5 times in each and make class dot plot how often did a difference of 7.7 or more occur. All right, blocking. Many students enroll in prep courses to improve their SATs. 20 students who have taken the SAT once volunteered to participate in an experiment comparing online and classroom prep courses. Describe how we can use a completely randomized design to compare online and classroom SAT prep courses. Well, we number students 1 to 20, use the random integer 1 to 20, generate 10 unique, remember repeating numbers ignored, that is important. The first 10 numbers selected correspond to students who will take the online course and the remaining 10 students will take the classroom course. Among the 20 volunteers, 10 are in pre-calc, 6 are in algebra 2, 4 are in geometry. What problem does this cause? Well, students in more advanced classes will likely improve more than students in lower level classes. It adds extra variability. We're talking pre-calculus to geometry. There's a wide range of knowledge separating those two classes. Hopefully, the random assignment event evenly spreads the students from each math class to each treatment group. And again, hopefully, we don't want to be hopefully, we want to make sure that we can arrange that or check that. Here are the results of the experiment using math levels as a blocking variable. Make dot plots to compare the improvements of the students in the online course and blah, blah, blah. You can tell that online did a little bit better because besides that point, if it was here, we would have just shifted by 20, 20 points. So it's showing a little bit. There's quite a bit of overlap, meaning the difference in mean improvement for classroom and online classes is not statistically significant. It's just be random. They're that close, and they're in the same pattern. Dot plots in number 3 ignore the fact we blocked my math level. Here's the dot plot again. The different symbols for all the different groups. And what do you know? Either classroom or online, we have the same 5 people doing about the best, and those are our pre-calc students, which makes sense. Our geometry students were lower. And so we're looking at all these groups. Together, we can compare these two, classroom and online, but we're also looking at the math or blocking level that is important. So notice that within each math level, the online students clearly did better. We couldn't see this difference when we ignored the blocks. The average improvement for students in pre-calc was 86, algebra 2 40, and geometry 20. How can we use this information to account for the variability created by differences in the class field? Subtract 66 points from pre-calc. Subtract 20 points from each algebra 2. So we're all kind of on the same page. Blocking experience is similar to stratification and sampling. We put things together and then we apply the treatment to half them in each group, and we apply our placebo or the other treatments or the different levels of treatments to the other group. Blocking accounts for a source of variability, just like stratifying. Means that blocking is a good way to increase power, make more precise. Blocks should be chosen like strata, based on some common characteristic. And they should be as similar as possible, but different from the other blocks. Blocks like strata are not formed at random. We chose it on purpose. What are some variables that we can block in for the caffeine? Health, best blocking variable, best predicts the response variable. So obviously your health is going to mess with your pulse rate in the first place, or caffeine, sorry. All right. Popcorn lover wants to know if it's better to use the popcorn button on the microwave or the recommended time on the bag of popcorn, because we have nothing else to do apparently. To measure how well each method works, we'll count the number of unpopped kernels remaining after popping. She goes to the store and buys 10 bags each of 4 different varieties of microwave popcorn. Movie butter, light butter, natural, and kettle corn, for a total of 40 bags. That's why a randomized block design might be referred to a complete randomized design for the experiment. Well, complete randomized ignores the difference between the 4 types of popcorn, which I'm sure will have some effect on how many pop, so which will probably result in a great deal of variability in the number of unpopped kernels. Randomized block design considers each variety of popcorn separately, which allows us to account for variability in number of unpopped kernels created by difference in varieties. So not only are we more specific with our groups and we can compare them, but we can now kind of have that data for 4 separate groups where we can compare within each group. And outline a randomized block design for the experiment. Randomly assign 5 bags of each popcorn type to 2 treatments. Button versus instructions. For random assignment, place all 10 bags of particular popcorn in a large bag, shake and choose 5 randomly for popcorn button, and remaining 5 bags popped using instructions. Repeat process with each type of popcorn. Count the number of unpopped kernels in each bag and compare results with each person type. Combine results for each type after accounting for the difference in average response for each type. So you can see all the detail that we had to have in that. You need to be as specific. I keep using that word. You really need to be specific. Read it to your parents or friends, and if they know what you're talking about, it's probably good. We have block design, like we talked about. Matched pair design is basically the same thing, but there's just 2 treatments. 2 similar people, maybe twins, same person, right arm, left arm, comparing those are obviously pretty the same. Same person, do different days or pre-test, post-test stuff. So again, you're blocking, but there's only 2 groups. Could we use a matched pair design for the caffeine experiment? Yeah. Similar groups of people, same people on 2 different days. And that is our 4.2.